All right. So now when we're dissolving something or doing the dissolution of something, all right, dissolving it or dissolutioning it. Um, uh, let's talk about some of the things that work if we do that. First of all, if we have some water, say here we have water here, we're going to put, it says sucrose, I'm going to put salt just because I want to do salt instead of sucrose. But I put salt in here, all right, and it has a certain amount dissolved in it. Then I add more salt in it, and it still dissolves. That means back here I had less than the maximum amount, okay? Less than the maximum solute that it could dissolve. It can dissolve more. So this is considered unsaturated. Unsaturated means you're dissolving less than the maximum amount of solute in the liquid, okay? And so that would be an unsaturated solution because it's not full. Saturated, the idea of full or it can't hold anymore, and it can still hold more, so it's unsaturated. But if I keep it at the same temperature and I keep adding salt or sugar or whatever I'm adding to it, eventually it's going to reach the point where it starts settling down here at the bottom. In other words, it's saying, I can't hold anymore. That's all I can do. That is a saturated solution. It has the maximum amount of solute that it can hold, at least at that temperature. Now, if you were to change temperature, then it could probably hold more or less or whatever. If you change the temperature, that's going to change how much it can hold. But at that temperature, that's the most it can hold, so that's considered the saturated solution. It can't hold any more at that temperature. Okay, so that would be a saturated solution. All right. Now, saturated and unsaturated are general ways to describe solutions, and they are useful, but as we just pointed out, they depend on temperature a lot. If you increase the temperature, say you have hot tea, you can dissolve a whole lot more sugar in the hot tea than you could in the cold tea. And so if you ever try to add sugar to iced tea, you'll notice that's almost impossible. You can't hardly get it to dissolve. But if you add it to the hot tea first, dissolve it in there, and then cool it down with ice, then it will have a lot more sugar dissolved in it. Okay, and you won't end up with it all sitting at the bottom. So since it depends on temperature and some other things, maybe we should consider we need a way to measure how much is actually in the solution. Okay, not compared to how much you can hold, but just how much sugar or salt is actually dissolved in there. And in chemistry, when we try to measure the amounts of things, we use units called moles. Now, moles are not little furry things that get in your lawn, although I do have some of those at my house. Okay, in chemistry, a mole is equal to 1 mole is equal to 6.02 times 10 to the 23rd of something. Okay? In the same way, we might say that a dozen is equal to 12 of something, and I could have a dozen desks or a dozen students or a dozen anything, cars, whatever. Okay? A mole is the same kind of thing. It's talking about that many of something. 6.02 times 10 to the 23rd. How much is that? Well, 6.02. We move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 23, I think, if I counted correctly, that's about it. Okay, no decimal anymore. We're just saying that's how much of something we have. That's a bunch of something. Okay. Now, keep in mind, atoms are extremely, extremely small. So this many atoms might be held in your hand. Okay. Or it might take a small glass or something. But this is a lot of atoms. And it just tells you how small atoms are, that we have to measure them in units that are so big as moles. Because if you look at this, there's thousands, there's millions, there's billions, and there's trillions, and we're not even halfway there yet. And then we go into whatever after trillions, zillions, and quadrillions, and all those other ones we used to make up. But it's almost like a trillion trillions. Okay? That is a bigger number than we can really comprehend. Okay? And that's how small atoms are. If we had pennies, we stacked up this many, one bowl of pennies, it would reach all the way across the Milky Way galaxy, not across the Earth, not from the Earth to the Sun, but all the way across the entire galaxy. That's how big that would be. If we had a bowl of marbles and we spread them out, maybe we had a wall around the United States to keep them from running in the ocean, okay, or into Canada or Mexico. We finally built a wall. This is an imaginary wall, though. And we put that up, and we put a mole of marbles in there. It would reach a half a mile high across the whole United States. That's a lot of marbles, okay? So just give you this is an extremely enormous number, and that tells us how small atoms must be for us to be able to hold that many in our hand very often, depending on what it is, but about that many of them, 6.02 times 23, we can hold that many atoms in our hand or in a small glass or something like that. Okay? So that's a mole. If you have a mole of something, okay, say I have, in terms of sucrose or sugar, it would be 342 grams of sugar. Okay? And that would be equal to this many molecules of sugar. Okay, there are that many molecules. If it was salt, it would be sodium chloride, and it would be however many grams, roughly about 57 grams, because salt molecules don't weigh as much. Of salt would be a mole and would have this many atoms in it down here at the bottom. We would have that many atoms in it if it were a mole. Now, when we express that, if you have this many atoms in something, it is expressed in moles per liter. The abbreviation for mole, by the way, is MOL, which saves you a whole letter, so it's a really good abbreviation. But anyhow, just for the record, if I ever put MOL, that's what it stands for. It's just mole. Okay, how many moles per liter? So if you had this many atoms in 1 liter of water, which is, well, you know what a liter Coke bottle would be, okay, that would be a 1 molar solution, and usually we just write that 1 capital M. Okay, if we had twice as many, if we had 12.04 times 10 to the 23rd, then we would have a 2 molar solution. If we only had half of this, 3.01 times 10 to the 23rd, then we would have a 0.5 molar solution. Okay, and so based on how many moles per liter it would be, then that would tell us what the molar solution. If I had 1 mole of this in half a liter, which would be 500 milliliters, then that would be a 2 molar solution, because per liter it would be 2. It would take 2 moles to make a whole liter of that concentration. And this is a very precise measurement about the concentration of a solution. And so that is how we add, or how we measure concentrations of solution. Now, we mentioned that there are some things that affect the how soluble something is. Okay, so soluble depends on how solubility of something is how well it dissolves. Okay, if we talk about the solubility, we're just talking about its ability to dissolve, basically. All right. My spelling needs a little work here. So we can go back to that. There we go. Soluble. Let's see. Solubility of a substance just means how well a solute will dissolve in a particular solvent. Okay, if it's highly soluble, then we would say it dissolves very well. If it's insoluble means not soluble, so it will not dissolve at all. Okay, for example, if you try to dissolve oil and water, they will not dissolve in each other. Okay, or at least not to any amount worth measuring. Okay, so if it barely or hardly at all dissolves, we would say that is insoluble. Now, that may depend on the solvent. Glass, if you put water in a piece of glass, you would not expect it to dissolve, so that's insoluble. We'd say the glass is insoluble to water. But if you were to put it in a solution of hydrofluoric acid, HF, hydrofluoric acid, it would actually dissolve the glass. Okay, styrofoam peanuts, for example, we say they're insoluble to water, because normally we think of in terms of water, because that's the most common solvent that we have. It's called the universal solvent because it's used to dissolve so many things. And styrofoam will not dissolve in that. But if you stick it in acetone, it will dissolve it. And if you let the acetone dissolve off, you will get a thin sheet of plastic left from the styrofoam. Okay, so whether it's soluble or not depends on what you're trying to dissolve it in. permanent markers, for example, are insoluble usually in water, but they might be dissolvable in alcohol, rubbing alcohol, or other type of acetone, or other type of things too. So whether it's really permanent or not depends on what you're trying to dissolve it with. But yeah, now how well something dissolves depends on several things. First thing, it depends on the attraction between the molecules. Okay? And this is what we talked about before. If you have polar molecules, in an earlier chapter, polar molecules will dissolve other polar molecules. And the stronger their attraction to each other, the positive and negative charges, then the better it will dissolve. Okay, and it will be more and more soluble. The less attracted they are, for example, if you put a nonpolar substance in there, okay, this nonpolar will not dissolve in the polar because there's no attraction between there. Okay. And so basically, just depending on the attraction. If they are attracted to each other, then they mix together and they will dissolve. But if not, they will not. For example, salt and sugar both have a high solubility in water because of the charges. We talked about sodium having positive and negative charges. The sodium ions are positive, the chlorines are negatives. And when you put them in water, which has the oxygen side, which is negative, and the hydrogen side, which is positive, then these will separate. Sodium will go to the negative side, the chlorine will go here, and they dissolve easily. So the bigger the attraction between them, the better they will, the less they will not. Oxygen, on the other hand, is two oxygen atoms stuck together. They share electrons, so one side or the other is not very soluble. The only time that happens is if they get near a negative side, then it repels the electrons over here, and they become a little negative, and this becomes a little positive. As an induced dipole we talked about, then it would be attracted for a short time, but temporarily. If something shifts here, then it may drift off away, and unless it gets snagged by another water molecule, it'll just leave the water molecule altogether. So oxygen has a very low solubility because it's not attracted to the water molecules very much. Okay. Another thing besides of that would be the temperature. We've already talked about that a little bit. Okay. Generally speaking, the higher the temperature, the more solute that can be dissolved. Okay, so more solute can be dissolved if we have a higher temperature. So generally, as you heat it up, the water molecules move faster. It breaks apart the solute faster, and it will definitely speed up the rate. It will speed up the rate at which it dissolves because the water molecules are moving faster, so they'll mix faster. But it will also become more soluble. You can dissolve, we always said, like we said earlier, more sugar in hot tea than you can in cold tea. All right. Now, some things make more of a difference than others. All right. The temperature may make a bigger difference in some substances than others. For example, here as you heat up the water, the solubility, here's the temperature. As the water gets hotter, you know, some things like this is sodium nitrate here, you can say that it greatly increases how much of it will dissolve. Okay, lithium chloride will also increase, not nearly as much, but some. Okay, calcium chloride will increase slightly, but sodium chloride, which is salt, really doesn't matter much. Okay, it did increase slightly, but you probably can't hardly even see it on the graph here. It will increase a little bit slightly, but very, very little. So, for example, a cold ocean can dissolve almost as much salt as a warm ocean. So temperature doesn't really affect salt too much, but it does affect some of these other types of salts, sodium nitrate, lithium chloride, potassium chloride. It affects them, but the sodium chloride, it doesn't affect hardly at all. Okay, so depending on the substance, how much. There are some chemicals that actually get less soluble as they get hot. Now, that's the exception to the rule, but there are some that do that. For example, calcium carbonate. Okay, as it gets hotter, it becomes less soluble. Okay, and so if you were to heat it up, it may actually get some of it start settling out and start making deposits. Okay, this is very often what you see